So this is lecture number 11 in this series on control systems 2. So far we have done two state space forms, the first companion form and the second companion form. Today we'll be doing the third form, the Jordan canonical form. So we can convert a transfer function to a state space model, while as we can obtain n number, we can obtain infinite number of state space models for a particular system. Uh, we are concerned with three important types: the first companion form, the second companion form, and the Jordan canonical form. Uh, the importance of these forms will be discussed later. First of all, we are only trying to see how to obtain these models. So, again, assuming we have a nth order transfer function, beta naught Sn plus beta 1 S minus n minus 1, so on up to beta n minus 1 S plus beta n divided by Sn plus alpha 1 Sn minus 1 plus alpha 2 Sn minus 2 plus alpha n minus 1 S plus alpha n. So this is our general nth order transfer function described by this transfer function. So in this case, we know this is equal to ys divided by us. Fine. So in the first two cases, in the first companion form, what we did was we separated the numerator and the denominator and derived two different transfer functions. We actually divided the transfer function into two separate transfer functions. The numerator was separate and the denominator was separate. In the second companion form, what we actually did was we cross multiplied the numerator and denominator terms and found out the output of the system in its frequency domain and obtained the block diagram of the model. Now in this case, what we'll be doing is we'll be using the partial fraction method fine. So we have any equation we can if we have any fractional term where our denominator is a quadratic equation, we can obtain its roots, and in terms of roots we can then derive the partial. You can use the partial fraction algebra for obtaining the Jordan canonical form. ठीक है, जो हमारी ट्रांसफर फंक्शन थी हमने इसको partial fractions using partial fractions we divided them into, we are obtaining the fractions of the denominator term. Therefore, ys will be equal to beta naught times u of s plus r1 by s minus lambda 1 u of s plus r2 s minus lambda 2 u of s plus so on rn s minus lambda n u of s. ठीक है, तो फॉर एग्जाम्पल हमारे पास एक इक्वेशन है g of s is equal to 1 divided by s square plus 3s plus 2. We know this is equal to 1 by s plus 2, 1 by s plus 1. Fine. We can therefore then say this will be equal to r1 plus divided by s plus 2 plus r2 divided by s plus 1. And using partial fraction method, we can then find out the values of r1 and r2. Normally we would write a divided by s plus 2 plus b divided by s plus 1. क्योंकि यहाँ पे a b c d matrices we are already using the terms ABCD for matrices in the state space form. So we try to avoid use of ABCD here. So you can obtain the partial fractions of this particular equation use in this fashion. तो ऐसे ही आपके पास अब एक nth order transfer function है. You are obtaining the partial fraction of the nth order transfer function. In case the numerator and the denominator have the same order, you start with this beta naught with the coefficient of the numerator of the highest order. So what we'll be doing is we'll now be modeling this equation number 1 using the block diagram algebra. So we have the equation y of s is equal to beta naught u of s plus r1 by s minus lambda 1 times u of s plus r2 by s minus lambda 2 times u of s, fine, plus so on up to rn by s minus lambda n times u of s. So using the block diagrams, we can therefore say y of s is equal to summation of you have a gain of beta naught. So this is your beta naught u of s, fine. उसके बाद आपका your second term r1 divided by s minus lambda 1 times u of s. So if I can represent this in this fashion. This is a positive feedback system. If you simplify this positive feedback system, you know that the answer of this will be g divided by 1 minus gh, where g is 1 by s and h is lambda 1. So after solving this, this will come out to be r1. This will come out to be 1 divided by s minus lambda 1. Then it will be multiplied with r1. So at this point, you will be getting r1 by s minus lambda 1 times u of s. Similarly, for rest of the terms, on r n divided by s minus lambda n multiplied with r n multiplied with us, you will be getting y of s will be equal to all these terms. Now, as we know that there will be again a set of n integrators, and after the integrator we can assign the variable term. So let this be x1, this be x2, so on, this be xn. Therefore, before the integrator we'll be having x1 dot, x2 dot, xn dot. So if we look at these block diagrams now, what will x1 dot be equal to? X1 dot will be equal to u plus lambda 1 x1, lambda 1 x1 plus u. What will x2 dot?
So screen frozen है.
क्या?
Screen frozen है.
आप रिज्वाइन कर लो यहाँ से तो ठीक है.
ठीक है.
1 second. 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 1 second So x1 dot will be equal to u of s plus lambda 1 times x1. Uh, so x1 dot will be equal to us plus lambda 1 x1. x2 dot will be equal to u of s plus lambda 2 x2. Lambda 2 x2 plus u. Say xn dot is the easiest of the three canonical forms. Xn dot will be equal to xn lambda n xn plus u. So ये आपके x1 dot x2 dot xn dots हो गए. We will put them in the state space form. ऐसे ही y will be equal to r1 x1. यहाँ से जो आपका आउटपुट है r1 x1, then यहाँ से आपका r2 x2. So y will be equal to r1 x1 plus r2 x2 plus r3 x3 so on up to rn xn plus beta naught times u. Fine. These equations in the state space form. In the state space form, x1 dot, x2 dot, x3 dot, so on up to xn dot will be equal to something times x1, x2, x3. x1, x2, x3, so on up to xn plus something times u, and y will be equal to x1, x2 up to xn plus something times u. So x1 dot was lambda 1 x1 plus u. That means lambda 1 x1 plus 0 lambda x2 plus 0 x3. बाकी सारी टर्म्स 0 होंगे प्लस 1 टाइम्स u. ऐसे x2 dot was lambda 2 times x2. That means 0 lambda 2 0 1 times u. x3 dot will be 0 0 lambda 3 1. So all these terms, rest of the terms in this system will be zeros, while as the diagonal elements will be lambda 1, lambda 2, lambda 3 up to lambda n, where lambda 1, lambda 2, lambda 3 they were actually the roots of this characteristic equation. That means they are actually the eigenvalues of these matrices also. So lambdas are the roots of the characteristic equation of this transfer function or the eigenvalues of this matrix, because this is a diagonal matrix, so you can directly say these lambda 1, lambda 2, lambda 3, they are all the eigenvalues of this matrix A. Whereas y is equal to r1 x1, r2 x2, r3 x3, so on up to rn plus beta naught times u. So this is the Jordan canonical form. It basically represents your transfer function in a diagonal form. So diagonal form you can directly say what will be the eigenvalues of this system. So I think eigenvalues of matrix A will be lambda 1, lambda 2, lambda 3. So if these values are negative, that means our system is stable. So Jordan canonical form directly gives you the eigenvalues of the system. So just by looking at the Jordan canonical form, you can say whether your system is stable or not. Fine. Let's say we have a system s plus 2 divided by s plus 3, s plus 4, s plus 1. Fine. So we want to find out the Jordan canonical form of this particular transfer function. So we'll start by we'll use the partial fraction algebra to basically obtain the values of r1s first. So we can say s plus 2, s plus 3, s plus 4. By partial fractions, we can reduce the system to r1 divided by s plus 3 plus r2 divided by s plus 4 plus r3 divided by s plus 5, s plus 1. Fine. So in case the order of the numerator is equal to the order of the denominator, then this will actually start with the coefficient of the highest order of the numerator. क्योंकि यहाँ पे आपका numerator का order denominator के order से कम है, so we can directly write that this will be equal to r1 divided by s plus 3 plus r2 divided by s plus 4 plus r3 divided by s plus 1. So that means s plus 2 divided by s plus 3, s plus 4, s plus 1 is equal to r1, s plus 4, s plus 1 plus r2, s plus 3, s plus 1 plus r3, s plus 3, s plus 4 divided by s plus 3, s plus 4, s plus 1. Fine. So which implies s plus 2 is equal to s plus 2 is equal to r1, s plus 4, s plus 1, this whole thing. So if we substitute s equal to minus 3, that is minus 3 plus 2 is equal to minus 3 यहाँ पे भी है, minus 3 यहाँ पे, ये दोनों टर्म जीरो चाहिए. Minus 3 plus 4 is 1, minus 3 plus 1 is minus 2, so this is minus 2 times r1. That means r1 is equal to minus 1 divided by minus 2, that is equal to 1 by 2. Fine. Let's say let s equal to minus 1 if s is s equal to minus 4 rather. अगर s हम minus 4 कर देंगे तो minus 4 plus 2 minus 4 plus 2 is minus 2 is equal to 0, 0, minus 4 plus 3 that's minus 1, minus 4 plus 3 minus 4 plus 1, which implies r2 is equal to 2 divided by 3 minus times, and let s equal to minus 1, that gives us r3 and r3 will come out to be equal to 2, 3, 6, 1 divided by 6. तो ये आपके r1, r2 और r3 हो गए. तो आपका बेसिकली जो g of s है, जो आपकी ट्रांसफर फंक्शन है, that comes out to be equal to r1 that's 1 by 2 divided by s plus 3 plus s plus 4 plus s plus 1. So r2 was minus 2 by 3. So ये आपका GS है. So you can directly now say x1 dot, x2 dot, x3 dot will be equal to something times x1, x2, x3 plus something times u, while as y is equal to x1, x2, x3 plus something times u. फाइन. तो यहाँ पे बीटा नॉट तो ज़ीरो है, तो ये ज़ीरो ही आएगा. दिस विल बी फिल्ड बाय द lambdas, lambda 1, lambda 2, lambda 3. But lambda 1, lambda 2, lambda 3 are actually the negative terms यहाँ पे. तो ये minus 3 है, minus 4 है, minus 1 है, बाकी सारी टर्म्स इसमें ज़ीरो हैं. जो हमारा ओरिजिनल इक्वेशन था डैट उसमें डिनोमिनेटर s माइनस लैम्डा 1 था, दैट मीन्स लैम्डा 1 इज एक्चुअली बेसिकली माइनस 3. ऐसे ही आपका जो u मैट्रिक्स है और जॉर्डन कैनोनिकल फॉर्म b मैट्रिक्स इज 1, 1 एंड 1, while as y matrix is r1, r2, r3, that means numerator के जो कोएफिशिएंट्स है minus 1 by 2, minus 2 by 3 and 1 by 6. So this is your Jordan canonical form of this transfer function. तो आपको पहले स्टेप आपका ये कि पहले आप पार्शियल फ्रैक्शन करो ट्रांसफर फंक्शन का, अगर वो वहीं से पार्शियल फ्रैक्शन फॉर्म में दिया हुआ है then you can easily find out. If it is not given, you have to first reduce it into the partial fraction form using the partial fraction method, and then uh, find out also the numerator values and fill the C matrix. तो ये आपका जॉर्डन कैनोनिकल फॉर्म हो गया. अब इसमें एक स्पेशल केस है जो कि, and what is that special case? Say for example, you found out that your system has आपका कोई सिस्टम है, न्यूमरेटर डिवाइडेड बाय डिनोमिनेटर में बेसिकली से फॉर एग्जांपल यू हैव रिपीटेड रूट्स. ठीक है, you have two roots that are repeating. You have s plus lambda 1 का square. That means this is actually s plus lambda 1 and s plus lambda 1. So इसमें lambda 1 or lambda 2 they are basically repeating. So that means you have to find out in this case what will happen to the system. ठीक है, so when you will obtain the partial fraction of this system, you will see that you can break it down into this thing. जब हम partial fraction करते हैं repeated roots का, the method is a divided by s plus b divided by s square. फाइन, तो यहाँ पे आपका s माइनस लैम्डा 1 है और s माइनस लैम्डा 1 स्क्वायर है. So when you will do the partial fraction of a system that has repeated roots, you will obtain this type of partial fraction r1 divided by s minus lambda 1 to r2 divided by s minus lambda 1 square. So then you have to model this system. So इस केस में क्या होगा, let me redraw it. So you have this system now. Now you have to draw the model. You have to draw the block diagram of this particular model. So y of s is equal to बीटा नॉट ऑफ u of s. वो तो वैसे ही रहेगा. उसके बाद r1 divided by s minus lambda 1 times u of s. ठीक है, and then instead of the second term is what, r2 divided by s minus lambda 1 square. So this is actually y of s divided by u of s. u of s अगर आप इस साइड ले जाओगे तो ये सारी आपके साथ मल्टीप्लाई हो जाएगा. ठीक है, so when you will pass this same this signal through this point y, so ये 1 by s minus ये 1 by s स्क्वायर 2 बार आ जाएगा. तो देन यू कैन असाइन नाउ x1 x2 x3 सिमिलर इन द सिमिलर फैशन. बाकी टर्म्स सेम रहेंगी. बाकी टर्म के साथ हमें कुछ नहीं है. बाकी टर्म्स में कोई there is no change in the rest of the terms. Depending upon the number of roots that are coming out to be equal, accordingly आपके सिस्टम में चेंज आ जाएगी. Depending upon the number of equal roots, in this particular case, what I have done is I have taken two equal roots. So instead of this signal, ये जो सिग्नल नॉर्मली u ऑफ s से आ रही थी, अभी यहाँ से आएगी क्योंकि ये इसको 1 बाई एस माइनस लैमडा 1 स्क्वायर, ये जो सिग्नल यहाँ से आ रही है दिस इज 1 बाई एस माइनस लैमडा 1. ये ट्वाइस जब यहाँ से यहाँ तक पहुँचेगी, ये 2 बार 1 बाई एस माइनस लैमडा 1 आएगी. डैट मीन 1 बाई एस माइनस लैमडा 1 स्क्वायर बन जाएगी. फिर उसको R2 के साथ मल्टीप्लाई किया एंड अकॉर्डिंगली वी हैव ऑब्टेन द सिस्टम आउटपुट. नाउ अब इसमें यहाँ पे आप x1 को x3 x1 और x2 में अब कंफ्यूजन हो सकता है. वेदर यू डिनोट दिस एज x1 और दिस एज x1, इसको x2 करोगे. x3 x4 x5 up to xn they are same, or you can denote this as x1 and this as x2, x3 x4 x5 बाकी टर्म्स तो सेम रहेंगी. so accordingly if you are choosing x1, से फॉर एग्जाम्पल हम बोथ केसेस देखेंगे. से फॉर एग्जाम्पल मैं इसको x1 लूँगा और इसको x2 लूँगा. x3 x4 x5 बाकी सारी टर्म्स सेम है. तो x1 डॉट मेरा ये है यहाँ पे. x1 डॉट इज सिंपली लैम्डा 1 x1 प्लस u. x2 डॉट इज x3 dot will be lambda 3 x3 plus u. x4 will be same. xn dot will be lambda n xn plus u. Fine. अब x2 dot लेकिन क्या होगा यहाँ पे? x2 dot is this term. x2 dot क्या आ रहा है आपका? x2 dot is equal to x1 plus lambda 1 x2. x2 dot is x1 plus lambda 1 x2. Fine. In case I denote this as x1 and this as x2, मेरा x1 dot और x2 dot ये आएगा. बाकी x3 x4 सारे सेम रहेंगे. In case I denote this as x1, that means this is x1 dot and this is x2 and this is x2 dot. In that case x2 dot will be equal to lambda 1 x2 plus u, while as x1 dot will be equal to x1 dot will be equal to x2 plus lambda 1 x1. ठीक है, तो ये आप तक है. इससे बेसिकली वी कैन यूज एनी ऑफ द टू फॉर्म्स. तो पहले फॉर्म में x1 डॉट x2 डॉट x3 डॉट सो ऑन अप टू xn डॉट. y में कोई चेंज नहीं आएगी. y आपका फिर भी वही आएगा, r1 x1 प्लस r2 x2 प्लस r3 x3 सो ऑन अप टू rn xn. x3 dot same है. x3 dot is same in both cases. x4 dot is same in both cases. तो यहाँ तक तो कोई डिफरेंस नहीं है. इन द बाकी के रोज में कोई डिफरेंस नहीं है. x3 डॉट से लेके xn डॉट तक ये यहाँ से 1 1 1 है. x1 डॉट इन द फर्स्ट केस, ठीक है, ये इसको मैं फर्स्ट लेता हूँ, इसको मैं सेकंड लेता हूँ. इन द फर्स्ट केस x1 डॉट इज लैम्डा 1 x1 लैम्डा वन एक्स वन प्लस यू, दैट मीन्स बाकी की टर्म्स इसमें ज़ीरो है, ये वन आएगा यहाँ पे। x2 dot in the first case part is equal to x1 plus lambda 1 x2, x1 plus lambda 1 x2, बाकी की टर्म ज़ीरो आएंगी और ये भी ज़ीरो आएगा। इन द सेकेंड केस अगर मैं x1 डॉट और x2 डॉट को स्वैप करता हूँ, in the second case x1 dot is lambda 1 x1 plus x2, that means ये lambda 1 आएगा, ये 1 आएगा, बाकी की टर्म ज़ीरो होगी। lambda 2 will be 0 times x1, lambda 2 तो है नहीं, lambda 1 ही है, 0, ये 0 0, lambda 3 up to 0 zeros up to lambda n, ठीक है। So this is a case of repeated roots। ये आपका 0 1 1 1 so on up to 1 आएगा। So you can write either way, you can either यहाँ पे देख सकते हो आप, या तो ये 0 और 1 होगा, या तो ये 1 और 0 होगा, और अकॉर्डिंगली या तो ये 1 और 0 होगा या तो ये 0 1 होगा। दिस इज द केस ऑफ रिपीटेड रूट्स। यहाँ पे जो मैंने केस लिया था, मैंने 2 रिपीटेड रूट्स का केस लिया था। यू कैन हैव 3 रिपीटेड रूट्स, यू कैन हैव 4 रिपीटेड रूट्स, यू कैन हैव कहीं लैम्डा 1 भी रिपीट हो सकता है, लैम्डा 2 भी रिपीट हो सकता है, लैम्डा 3 भी रिपीट हो सकता है। तो अकॉर्डिंगली आपके जो फॉर्म्स है वो चेंज हो जाएंगे। In case this is for 2 repeated roots, in case of 3 repeated roots, उस केस में क्या आएगा, यहाँ पे भी 0 होगा, यहाँ पे 1 आएगा, ठीक है। एंड दिस विल बी लैम्डा 1 बिकॉज देन आपके 3 रिपीटेड रूट्स हैं। ऐसे 4 रिपीटेड रूट्स होंगे, फिर ये 1 1, ये जो एक्चुअली यू मैट्रिक्स का 1 होता है वो ए मैट्रिक्स में शिफ्ट हो जाता है। यू कैन रिमेंबर इट लाइक दिस, फाइन। So this your normal Jordan canonical form is this. This is your normal Jordan canonical form. In case of repeated roots, say for example lambda 1, lambda 2 and lambda 3, they are equal. You can either change these ones or you can change these into ones. एक ही बात है. So you can say for 3 repeated roots, this will be 1, this will be 1, while as these are all equal to lambda 1s, and accordingly ये 0 बन जाएंगे, फाइन। तो ऐसे आपका फिर लैम्डा 2 भी रिपीट हो सकता है, आपका लैम्डा 5 भी रिपीट हो सकता है। यू कैन हैव डिफरेंट रूट्स रिपीटिंग इन द सिस्टम and you have to accordingly see what will be the Jordan canonical form. You can go for either of the two forms, जैसे मैंने आपको बताया x1 डॉट किसको आप रिप्रेजेंट करोगे या किसको नहीं रिप्रेजेंट करोगे। अकॉर्डिंगली या तो 1 अपर ट्रायंगुलर मैट्रिक्स में होगा या तो 1 लोअर ट्रायंगुलर मैट्रिक्स में होगा, ठीक है। एंड अकॉर्डिंगली आपका ये 1 0 होगा यू मैट्रिक्स या 0 1 होगा, फाइन। You can write in either of the forms for a repeated root, ठीक है। So this is the case of repeated roots, and if I take an example, that g of s is equal to s plus 3 divided by s plus 2 square into s plus 5. So after partial fractioning this, you will obtain 14 by 9 s plus 2 plus 1 by 3 s plus 2 square plus minus 2 by 9 s plus 5. So the Jordan canonical form, इसका जो A मैट्रिक्स होगा, एक तो आपके यहाँ पे -2 -2 -5 आएंगे। Now you can either write this as 1 or this as, क्योंकि repeated roots हैं, अकॉर्डिंगली जो आपका बी मैट्रिक्स होगा दैट विल बी 1 0 1, और आपका जो सी मैट्रिक्स है इस केस में दैट्स 14/9, 1/3 एंड -2/9. Fine. So this is your Jordan canonical form for repeated roots. So that's all for today. If you have any questions.